So back here, so here we have, again, the definition of a differential equation, the order, and so I want to give an example here of a differential equation, something that we've seen and something simple, and talk about the solution. So here is a first order differential equation, dy dx equals x plus 1. It's an equation that has a derivative in it. That's it. Again, a whole course is dedicated to some of the strategies to solve these. We're going to see some of these today. And the first thing is just connecting this to where we have been. So if I would say solve this differential equation, what I'm really saying is tell me what y is. Right? So tell me the function whose derivative is x plus 1. That should be easy. Should be able to do that real quick. Look at your neighbor's paper, make sure they didn't forget something. There's an obvious thing that people forget all the time in this question. What do people forget? The C, yes. So hopefully you have this. Okay. Now, this is given a name when we're talking about differential equations. This is the general solution. The general solution. I think about it or talk about it sometimes as a family of functions. Now, when I say family of functions, I hope you almost think about like maybe in trig is the first time you start talking about, well, if the parent function is x squared, how does this other thing transform it, move it, left, right, up, down? And so that's really what we have here. We have a bunch of parabolas that are related by a shift, right? That's what the C would do, shift it up and down. Now, if I would say this, y of 0 equals 3, this information we were using previously to basically to get C, right? And so if I do that, what is the solution now? Go ahead. Plus 3, yeah. So this is really, remember this is a point. That's the x value, that's the y value. We're going to substitute, etc. Done. Now this has another name. This is referred to as the specific solution. Specific solution. Somebody silence that for me too. Old news, right? Things we've seen. New language, but same solving really. So let's do another one. So if I would say a prime of x equals I'll be nicer to you. If I say this, and then I say this, find the specific solution. So I have a differential equation involving derivative. I have a point on the original function. Really the antiderivative, I hope, is what you're thinking. I'm sorry. I was trying to help you out by doing that. Can I change this? Makes the C worse. Oh, this one's wrong. Sorry, I was just trying to sketch it down real quick. So, antiderivative, increase the power, divide by the new power, increase the power, divide by the new power, et cetera, et cetera, et cetera. Do that again. Now substitute in 1, and then solve for C. Do that real quick. Have you figured out C? Nine over 32. Okay. Do you have C yet? What is it? 7 minus 1/32. I think you could do better than that, but like I hope everybody's doing this, that they're saying 6 then equals 1 minus 2 plus 1/32 minus 2 plus 2. So Seth's right. He just didn't give me a final fraction here. So there's our answer, just arithmetic. We good with finding this antiderivative? Okay, so I want to make it more difficult here, more related to the fundamental theorem. So if I say this, g prime of theta is the cube root of the tangent of theta, and g of 0 equals 4. I'd like you to write g of theta. Now, the first thing that you should probably consider is that, wait a minute, I don't really know the antiderivative here. Well, do you? But didn't we spend the whole last chapter talking about how to write the antiderivative using an integral? So think about it maybe this way. Like we talked about how you could type something into your calculator that would see the antiderivative. That's what I want you to write. So what integral could you write here that would be the antiderivative of this function? Try it. Let's see how you did. Again, it'd be best if you didn't use theta where those x's are. Because then in just a minute, if I would say like find g of 2, it would look really confusing. We wouldn't be sure what actually is 2. So those of you that are still looking at this and like, well, I'm still not sure why that works. I'm just going to show this one more time. if I wrote it this way, and I think about this as really a number here, so I'm going to subtract it to the other side. Do you notice what I'm writing is actually just the fundamental theorem? This whole thing is really G prime. You see that that's exactly the fundamental theorem, just rearranged? Because wouldn't I find the antiderivative of capital G prime? Isn't that capital G then? It's the function that's not the derivative. Substitute in the upper limit minus substitute in the lower. Okay, so how many of you got this one right? Okay, good. Real quick, scale of 1 to 5. Where are you on everything I've said so far today? Okay, thank you. So, lots of 4s and 5s, which is good. So how does this change into something new in Chapter 7? So what we're going to look at today, and this is how you can title all of your notes for today, you can title it Slope Fields. Slope Fields. Even when I say that, maybe you think of a few things, like, did you ever do the little lab in science class where you took a magnet and you shook little iron shavings around it and you could see which way the shavings were oriented and you could see the magnetic field, right? But so maybe you've seen drawings of electrical fields, and so we're going to be drawing something that looks like those today. So the first thing is, I want to start with a differential equation that we already solved. So jot this one down again. And in relative decent size on your paper, I want to put some tick marks that go left and right, up and down 2 units. So scale these out nicely. And I want to put a point at each integer here, okay? So we have 25 little dots here. And we're going to start constructing, a slope field. Now to do this, we just really need to remember what a derivative is. Like, so when we write dy dx equals something, I don't really care what that is right now. Like, what am I saying? Like, what is this statement telling us? It is telling us what? Yes, so it's the slope of some function at x, right? That's what the derivative is. It's the slope of the tangent line, slope of the function, slope of the curve, at whatever x is. It's the formula for all of the slopes. So now for us, we know the function, right? So we've actually already wrote down this antiderivative here that we know is connected. So I'm just going to kind of put this in parentheses here, so I'm kind of thinking about it. But the goal really of the slope field, and so I'm going to kind of put this off to the side. So the slope field will help us see the solution to the differential equation. I'm going to say this differently in a minute, but we already know the solution to this differential equation. It's 1/2 x squared plus x plus c. So the slope field is a way to help us see that solution. Okay? So here's how it works. Seth said this is a formula for slope. Maybe before I do that, maybe I pause for just a second. So before I do that, you don't have to draw this, but I just want you to imagine something. If I put the solution, put the solution here, just this parabola, pick a C value, I draw it in. So let's say I'm looking at this parabola, and this is first semester. And I start thinking about tangent lines. And I think about a tangent line here. But then I think about a tangent line here. And I think about a tangent line here. And here. And here. If I draw in a bunch of tangent lines, do you notice that I can erase the curve and you can still get a really good idea of the function that I was thinking of, right? So that even just in this terrible sketch, right, you can look at this and go, yeah, I kind of can tell that you were drawing something like this, right? So imagine what we're going to do here is try to understand the slopes to help us understand the curve that made the slopes, okay? And that's what a slope field is. So here's how that works. I'm going to go back here. I'm going to choose just like this point. Now that point is the ordered pair 1, 2. Okay? So what does this formula state the slope is at the point 1, 2? Not hard. What is it? It's 2. X is 1, right? So in other words, if I think about the solution for a minute, again, it's only because we know the solution that I'm doing it this way, that isn't there some parabola, a certain C, that's going to send it through that point? Right, there's some shift of C, like if you think about that parabola, that's going to go through that point 1, 2. Now, what we are then saying is that the slope there at that point should be 2, because the x value is 1, so we're just substituting that in. Now, here's the issue. So I'm going to delete the solution because we're trying to see the solution. But it's going to get really messy if I draw my tangent lines going across the whole kind of field, right? Because I'm going to draw another tangent line other places, and I'm really just going to end up with lines that are going everywhere, and I'm not going to be able to kind of see the shape anymore. So what we're going to do, instead of drawing the full tangent line, I'm just going to draw a little piece of it. So just a little segment, but in my head, I'm thinking, okay, yeah, there was some tangent on the whole thing, but I don't want it to overlap everywhere, so I'm going to delete part of it. Now, what is true about the slope at those 4 points I just circled? It's got to be the same. Now, that should really connect in your head to the plus C shift, right? If I move a graph up and down, I don't change its steepness. So all I'm going to do right now, if I'm just kind of estimating this, I'm going to try to draw just the same steepness. Same. Okay. So let me do another one with you, and then I'll have you finish it. So this point right here is the point 2, 2, sorry. Well, the slope there, so if the parabola would be going through that point, like there's some parabola that's going to go through that point, the slope there should be what? Steeper, in fact, what number? It should be 3. So all I'm going to do is draw something that looks noticeably steeper. So if you're just supposed to sketch one of these by hand, like I just want to be able to look at that and go, okay, I can tell you're trying to make it steeper. Do the other 3 columns. Again, just kind of rough shape. So if you have finished that, do you notice something? like I had said, the slope field will help us, quote, see the solution to the differential equation. The solution to this differential equation is a quadratic. Can you see the quadratic? Now, to help us maybe better see it, okay, and to have a little bit more exact, I put this into the computer, okay, so that we can see the full slope field. Now, I will say the first moment of looking at it, it's a little overwhelming, so give your eyes a minute to kind of take it in. Now, I hope as you're looking at this, you see a bunch of parabolas that are shifted vertically from each other, right? Now, our solution, our specific solution to that first problem, what point was it supposed to go through? 0, was it 0, 4, 0, 3? It doesn't matter. Whichever, it was 3. Okay, so there is the specific solution. Do you notice that those little segments are following the curve? Which makes sense. If the little segments are tangent lines, then, you know, it's not going to like go through all of these. You'd expect, because if I would fill the whole plane with little segments, it would just all be filled in. You couldn't see anything. So, but do you see the tangent lines there, how well they're following the curve? So there is a specific solution. But notice if I change C, I get other ones, right? I can make this, I can shift this through all of these other points that we're noticing. Okay, so here's what I'm going to do. I want you to type something, or I'm going to type something. I want you to write this in your notes, and then I'm going to change something here and have you predict what I typed. So here's what I'm going to add on to this statement. When you connect, when you connect the segments of the slope field, you are drawing, there's more than one way to say this. So I'm going to start with the solution to the differential equation. Which is the antiderivative. When you connect the segments of the slope field, you are drawing the solution to the differential equation. You are drawing the antiderivative. Let me go back here and point something else out, and then I'll change something, and then I'll bring the lights back up a little bit. Just feel like it's a little difficult. It's a little easier with it being brighter to see this. Now, what I mean by connecting them, okay? So let's say I'm looking at this slope field, and I just put my pen down somewhere, okay? And I look at that segment, and again, this little segment right here is part of some tangent line. Doesn't that tell me how the curve is behaving right there? Right? In other words, can't I, if I think about locally linear, can't I kind of just follow these little segments and pretend that that is the curve? In fact, do you see it here? It's really like going to be parallel to this piece here. So when I say connect the dots, I'm really just looking at this going, okay, steep, not as steep, not as steep, not as steep. And I can kind of follow this and draw the solution, okay? All right, so here's what I'm going to do. I'm going to go back. And I'm going to change the differential equation, okay? So the one we were looking at was the one we knew the answer to, right? It was this. I'm going to go back and change it. I'm going to change it to one of these four things. And I want you to tell me which one I chose. So I'm going to type in to the computer one of these. Sorry, you can't see that. This. I'm going to type in one of these four things. Okay? I'm going to show you the slope field. And you're going to tell me what the differential equation was. Got it? So, give me 1 second. That was supposed to be negative. Yeah, it didn't mark it again. I don't know why my pen is skipping. Yep, so negative cosine. So sine, cosine, or their opposites. Okay, you are looking at a slope field. You are looking at a slope field generated by dy dx equals sine x, cosine x, minus sine x, or minus cosine x. One of those. Can you figure it out? Take a minute to do that. Okay, so here is, I hope, the pattern you're kind of noticing in the slope field. Now, I did not ask you the solution to the differential equation that you didn't know. The solution to the differential equation you don't know is some sine function that has a constant. But that's not what I asked you. I asked, what was the differential equation? What is the thing I would have typed in that would have produced this as a slope field? So it is not sine of x. That's not what I typed in. What do you think, Abai? Incorrect. It is not negative cosine. Yes? It is just cosine. It's just cosine. Now, why? Say that better. You're making it harder. You are making it harder. There's no capital G here. I don't know what capital G is. Say that differently. How do we know that this was cosine? It was the derivative of what you're looking at. It's the derivative of what you're looking at. Several of you that are saying negative cosine, you're thinking antiderivative, right? But remember that we're saying the differential equation, dy dx, isn't that the derivative of y? And when you're when you're drawing this pattern, like you're saying y equals, so really this says y equals sine of x plus c. What is the derivative of sine of x plus c? Cosine of x. So that means the differential equation was just cosine of x. Now, I highly suggest you take 30 seconds, write down something you just learned about how the slope field solution is maybe different than you first were thinking it was. Or this connect the dots, how they relate to the equation that is the differential equation. Dots, connect the dots, is the solution to the differential equation, which means it's the original y equals function, okay? So if I connect the dots and I see a function, the original differential equation should be the derivative of the connect the dots. Right? If this is y equals, when I connect the dots and see the sign of x, then the dy dx should be its derivative. In other words, then what you're looking at is the antiderivative of the differential equation. Right? So the antiderivative of the differential equation is what we see. So the derivative of what I see should be the differential equation. Timmy, do I connect there? Okay. Yeah, so I was asking it backwards. So this graph is the antiderivative of this cosine of x. Okay? And that's why I have a shift here that I don't know, right? Because it could be this one. It could be a different one. Right there. It's frozen. Right? It could be any of these shifts. But the derivative of all of these is still cosine of x, right? Because the shift doesn't matter. Now, if I did this, if I put a +1 here, this is not the same thing as a c. Because think about what I just changed. When I find this antiderivative, so any kind of constant in here in this differential equation, isn't this antiderivative going to have an x in it, right? I'm going to get a plus x, which is why I don't really see a lot here that helps me understand this. So let me zoom out a bit and remake it. Do you notice that this is going to kind of follow this kind of wave pattern, but it's going to be kind of moving along a line? New problem. I'm going to change this dramatically, something different, and then you need to grab your calculator real quick so you can learn how to put this in. So I'm going to type in negative, what do I type in? I want to type in negative x divided by y. Now, in just a minute, I'll show you how to do this on your calculator, but I want you to recognize that we have done things like this before. Okay? I don't know why this is like glitching here. I don't know why it's hiding that. Let me try again. There we go. So when you're looking at this, here's why this one is so different. Do you notice a minute ago when you were making these, like when you looked vertical, we just said, oh, they're all the same? They're no longer all the same. Seth? You're just going to have to deal with it. So, do you notice a pattern here in this slope field? Yeah, we should actually see a bunch of circles. Now, depending on the c value I choose, we could get the circle on the top half or the bottom half, right? Because thinking about really all of these concentric circles here. These kinds of things are definitely possible when I think about implicit differentiation, right? If you take the derivative of x squared plus y squared equals 25, well, that's exactly where this answer came from. We saw that first semester, okay? 2x plus 2y dy dx equals 0. Rearrange, this is exactly what we get. So I'm just pointing that out. So I wanted you to take your calculator, and I'll show you how to type in differential equations. Okay, so the first thing on your 89, what you'll want to do is to go to the mode. You don't have to do this on the Inspire, but on the 89, go to mode, and where it says function, you're going to go to differential equations. If you don't have an 89 or Inspire, you can't do this. You get to look online to try to find a online differential equation grapher. Okay? So I'm going to choose differential equations. I just said, what did I just say about the 84? Doesn't do it. So you're going to choose differential equations. And now go to the y equals menu. On the Inspire, just go to the graph menu. Okay? And when you're in the Inspire, you're going to hit that menu and you're going to choose, not that, get out of that. Hit menu. Graph entry edit, and then choose option 8, which is differential equations. Okay? Now, in both of these calculators, when that comes up, I don't know what happened to mine. Maybe I didn't hit save. Let me go back. Yeah, forgot to hit save. Differential equation, save. Okay, so I want to type in, let's say I want to type in that negative x over y. So on the 89, we have to type t's. On the Inspire, you're going to type x's. So we're going to type negative x, I'm sorry, I just said t. So negative t divided by, now on both calculators, like on the Inspire right now, it tells you what function you are inputting, right? It says y1 probably, or f1, does it say y? Yeah, it should say y1. And on the 89, do you notice I'm typing in y1? It says y1 prime, so I'm actually going to type y1. So on the Inspire, you're just going to type negative x divided by y1. Now, you're not dividing by itself because that's the derivative, right? So we're saying dy dx equals negative x over y. Go ahead and hit enter. Now, on the Inspire, there's a spot that looks like a point that you're going to put in, right? Do you see it? When you edit that graph, comes up below. And what we're going to do is we're going to choose a value. So here, that's what the 89 is. That's what this is, an x and then a y. So I'm going to say x is 4, y is, I don't know, 5. And then if I hit graph, what I should see are these concentric circles, and it's going to try to draw one solution. Okay? And that, I'm past time, thanks for sticking with me there, but that really is the start of our slope fields. You have homework from that packet. We will pick this up tomorrow.